They'll cede their points to you. It started? Yeah. Okay, cool. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just pray that you'd help us to understand a little bit more about your creation today. We pray that the students understand the implicit differentiation that we're going over. And Lord, just pray that you be glorified, Lord, when we do this day. In your name I pray, Lord Jesus. Amen. Okay, so I need to talk to you about what's known as implicit differentiation. And so what's the word implicit mean? Do you guys know? Like implicit versus explicit, what's the difference in these terms? Well, here's the basic thing is this. Implicit, if you implicitly define something, it's kind of the definition, differentiation. So if you implicitly define something, it could be wrapped up in something else. So it's like this, x squared plus xy cubed plus y squared equals 7. So this equation, all right, would implicitly define y as a function of x. I think I've had about enough of this marker. Watch out. What's an example of explicit? How about this? Y equals to x squared. This explicitly defines y as a function of x, right? You see that? What's the function? This marker isn't much better. Watch out, I might get hit you in the head. Oh, man. What? What?
Yeah.
I'm not sure where that water. Where's that water coming from?
We're good to baseball.
I don't know. All right. Fortunately, the math is waterproof. It'll be okay. So this is y explicitly as a function of x, right? In other words, the function is just sitting there. It's obvious. What if I was to write, if you were to say that this equation defines y as a function of x, like y equals f of x for what f, right? Can you tell me the function? Here, let me make it simpler. X squared plus y squared equals to 3. Here's another example of y implicitly being defined as a function of x. Can you tell me what y is equal to? Aha. So you're like, yeah, y is equal to, so I take y squared is equal to 3 minus x squared, right? And then I can take the square root of both sides, and I get the square root of 3 minus x squared, right? Well, that's not quite true, right? I mean, you should allow for, there could be a plus or a minus here, right? So, and you know, so what's this graph look like? It's a circle, right? And so the top of the circle is what? It's this piece. That would be the plus. And the bottom, right, is, oh, come on, where's my red marker? Worst throw ever. It's ruined my day. See here. Just, man. So there's the minus, right? So in fact, this circle, it's not the graph of a single function, it's the graph of two functions. Okay? So this example, the second example, let me call this example 1. I'll call this example 2. Good grief. Example 2. These are both, my starting point is to give you some equation, right? We have some equation which implicitly defines y as a function of x. Now here's the interesting thing. You can't always solve for y. Maybe you guys can, but I personally, if you ask me to solve this for y, I really can't do it. I can't isolate y. However, the technique of implicit differentiation, first of all, the technique of implicit differentiation is based upon this theorem of advanced calculus, which says that, you know what? When you got an equation like this, it turns out you can always solve for y as a function of x, in principle, even if you can't actually hack the algebra. So this is always possible, at least if you pick a point, right? If you pick some point on the equation like this, there's going to be some solution which passes through that point. So some sort of local solution to the equation. So that means that, at least in principle, y is a function of x, even if we can't find it. So that means I can differentiate. And so for example, the first example, even though I can't solve for y as a function of x, I can find dy dx. And how do you do that? So I take d dx of the equation. I take d dx of x squared plus xy cubed plus y squared. And that will be equal to the derivative with respect to x of 7. See what I did? So just differentiate both sides of the equation. And when I do this, I'm assuming that y is a function of x. Again, I can't actually find the formula for it, but who cares? So what's this derivative is what? 2x plus? Aha. So this one, one more step. I'm going to write one more step. Plus xy cubed. I'm going to leave it as a mystery. This one is 2y times dy dx. Now, why do I have dy dx there? I'm differentiating with respect to x. It's a function of y. So the chain rule applies, right? Well, you're like, well, what is dy dx? The thing we're trying to find. All right? So we're trying to find dy dx, like I said at the top. So then what? What's this? It's a product. I got to use the product rule, right? So that's 2x plus the derivative of x is just 1, so that's y cubed, plus 3x y squared, and then I've got dy dx by the chain rule. So can you find dy dx? You're like, yes, it's right here, right? But what I'd like for us to do is to solve for dy dx. Can you do that? So now our goal is to isolate dy dx. So we've got 3x y squared plus 2y, parentheses, times dy dx is equal to what? I'm going to move all the terms without the y prime. We can also call this y prime, which is easier to verbalize, right? What do you want to say in your mind? Y prime or dy dx? I don't know, whatever. But the reason I use dy dx in these calculations is that it's so easy to lose track of a y prime if you're not careful. It's a lot harder to lose track of dy dx, right? It's big in the notation. It's hard to lose. A prime is easy to lose in your calculation, so it's dangerous to use prime. I wouldn't take off points if you use y prime. I'm just saying it's harder to make a mistake if you use dy dx. And then I've got minus 2x minus y cubed, right? Now can you solve for dy dx? I think we can, right? sorry, water distracting me. Dy dx is equal to minus 2x minus y cubed divided by 3x y squared plus 2y. And there you have it. That's dy dx. Yes, sir?
I'm having a tough time realizing where you put dy dx, or the d over dx versus dy dx when like in the first and second line. Like, why did you put d dx next to the?
Oh, I'm differentiating this term plus the derivative of that term plus the derivative of this term. I want to emphasize that this is a product rule, so I have to, this guy right here splits into both of these terms in the next by the product rule. Yeah.
And then did you add dy dx because the last term was just y?
Right, because we're differentiating a function of y, the square function of y. The inside function is y, so I have to multiply by the derivative of the inside function. It's chain rule.
And if you were looking for the derivative of x, you would?
It would be like this. I mean, you could say, well, there's also a dx there. Well, that's true, but we don't have to write that because it's one. Yeah, go ahead. What's your question?
So why did you get rid of the y cubed when you're isolating dy dx?
Why did I get rid of the y cubed?
When you, the y cubed plus 3xy squared, that's all one of the different.
I mean, I subtracted y cubed from both sides of this equation, so that moves it over to there. And I grouped grouped the terms with dy dx, pulled the factor of dy dx out.
Okay.
Don't worry, we're going to do about 3 more examples. The algebra will be the same on each one. You'll start to pick up on what we're doing. Yeah.
So you use chain rule in the middle term, right?
Mm-hmm. We use the chain rule 2 times.
Okay, I guess on the middle term and the last term.
Right.
So on the first term, I should say it's now the second term, you have 2x plus y cubed. Why is it y cubed?
That's these underlined in blue. This is the product rule.
Oh, you can. All right.
Mm-hmm.
That's why I was confused. Like that doesn't look like I have the chain rule.
It's totally fine. Totally fine. Hey, let's look at let's look at example number 2 here. So again, I want to find dy dx. Now, this example has the advantage that we can find dy dx in 2 different ways, right? We could find it explicitly, and we can also find it implicitly because we have the explicit formula for y in this case. So we're going to find dy dx in 2 ways. We're going to find it implicitly, and we're going to find it explicitly. The second route is generally not possible because algebra keeps us from solving for y in most examples. So x squared plus, I take d dx of x squared plus y squared is equal to d dx of 3, right? So differentiate the given equation implicitly, which just means we're assuming that y is a function of x. So this gives me 2x plus what? 2y dy dx is equal to 0. And then we solve for dy dx. Let me just write it over here again, put a box around it, and there you go. Now, wait till you guys are caught up with me here. How would I do it explicitly? So let's say implicitly was part A, and this will be part B. So that was part A. It's part B. I solved for y equals to, on you guys' advice, plus or minus the square root of 3 minus x squared, right? So we can differentiate that, right? What's the derivative of plus or minus is either 1 or minus 1. You can just pull that outside the derivative, right? So this is really just plus or minus 1 over 2 times the square root of 3 minus x squared times what? Times minus 2x. By the what? Uh-oh. I haven't erased anything yet, so no harm is done.
Oh, is it?
Well, I just wanted to make sure I could actually see it. It's cool. It's fine. It's okay. So then what? Can you simplify this? This is what? This is just like minus, well, it's minus x over plus or minus the square root of 3 minus x squared, which is what? What was y? Math is math. If we do the calculation in a different way, we should still get the same answer.
Will you ask us to do one of the same problem explicitly and implicitly?
Probably not. I'm mostly interested in you understanding the new thing, the implicit differentiation. But of course there's basically two, up till now we've been doing everything explicit, right? Basically, what's the format of the question? Here's a function, differentiate it, right? So there's just a new wrinkle. Now I'm saying, here's an equation, right? This equation somehow defines a function, differentiate, define the derivative. Even though you can't solve for y itself, right? That's kind of the cool thing. You notice that the formula for the derivative involves both x and y. See that? Oh, sorry, I'm outside of the frame. See that the formula for the derivative involves both x and y, right? In the implicit setup. But in the case of explicit differentiation, you get a formula for the derivative which just has x in it. See that? So the implicit differentiation will give us formulas for dy dx that have both x and y in them. Why does this matter? What do we do with derivatives usually? What's the next standard question that you're asked? I don't think you guys are ready for that question yet. Let's do another. Give me an equation, any equation. How about this? X cubed y squared plus y equals to x. And then find dy dx. All right? What do we do? Step 1, differentiate the equation. With respect to x. Anytime we have an expression involving y, we pick up a dy dx by the chain rule. Yep.
I'm sorry, to go back to
Go ahead,
the
this one.
last, example.
Uh-huh.
So why we could find, we could solve for y for example 2 implicitly and explicitly for
Right.
example 1.
Example
Be able to-
Example 1, I can't do like part A for example 1. I can't solve for y. That's kind of my point. If you try to solve this equation for y, how do you do it? You've got a square and a cube at the same time. How do you isolate y there?
Okay.
Generally speaking, there are lots of equations that you cannot solve for one of the variables. You just can't do it. If you're a mathematician and you got some time on your hands, you can even prove it's impossible by elementary means. But we'll leave that to those silly mathematicians. That's kind of an old story, but you guys have the quadratic formula, right? So you can basically solve any quadratic equation for x. You can isolate the x, right? There's also a cubic formula. You can solve for x if you have like a cubic equation in x. You can isolate x. There's even a quartic formula. You can isolate x using like addition, subtraction, radicals. It turns out it is impossible to write a general solution to the fifth order equation in terms of radicals and subtraction and addition. This was proved in like 1830 or so. By, I guess in part Galois, and there's also this guy named Abel. Galois had all these ideas, but he was also a French, like a young French person who had kind of a hot temper, and he got in some political argument and got killed at like age 20. But his math lives on here. So anyway, I'm just saying it is a deep and interesting question as to when you can solve an equation for a variable. Fortunately, we don't have to do that. We just differentiate it. So like this, what do you get? Differentiating this equation, what do we get? I'm going to write it out symbolically here. Now guys, it won't be long here. We'll be doing what's called related rate problems. For the end of class, we'll cover the related rate problem. There we'll use implicit differentiation to solve real-world problems. So we need to try to figure this out so we can actually apply it. So what's this give me? This gives me 3x squared y squared plus 2x cubed y dy dx plus dy dx is equal to 1. Why do I only have dy dx terms on two of those things but not the other two? What's the difference? Right, we have two functions of y we end up differentiating. The one we apply the product rule, right? After you apply the product rule. So then what? Step 2, isolate the derivative. And we'll do the same algebra we did pretty much the last time. We'll factor out things that have dy dx's. So there's a 2x cubed y, and there's a 1. And then I subtract anything without dy dx to the other side. So I've got a 1 minus 3x squared y squared. And then we solve for dy dx, solve for it. So what do we get? Dy dx is equal to 1 minus 3x squared y squared divided by 2x cubed y plus 1. There it is. You starting to see the algorithm here? Step number 1, differentiate the equation. Right? Make sure to put a dy dx every time you differentiate the function of y by the chain rule. Step number 2, isolate everything with the y dx on one side and everything without it on the other side. Step number 3, divide by the coefficient of dy dx. Done. What is it? I see scrunching.
Yeah. I don't get how you can take out the 2x cubed y plus 1 when that's only attached to one of the dy dx.
Oh, use your imagination. So there's a 1 here.
Oh, no. Okay. Gotcha.
Yay.
Okay.
All right, so that term and this term became these terms.
So you can combine like that. Okay. That just seems weird to me
Hmm,
but
hmm,
I
hmm.
get it.
Okay, great. There's another example we should do. I haven't done one quite this flavor yet. I'm going to erase this stuff over here. I mean, the examples I've done so far, they're all kind of the same variety. Let me do one with a different letter. How about find dy dt given that, let's see here, y squared plus t cubed is equal to t squared. So what's our conceptual starting point here is apparently y is equal to some function of time. So this notation is popular in like engineering and physics and math to some extent. That when I write that means y can be written as a function of time, right? Yeah, t is playing the role x did before. So my step number one, differentiate both sides with respect to time, right? Differentiate with respect to time. So I'll write that down. d dt y squared plus t quantity cubed is equal to d dt of t squared. So what do I have to do on the, well, here I'll do the easy part. 2t. Okay, I got that. I got that covered. How about the left-hand side, though? What are you looking at on the left-hand side? Chain rule, right? So the whole thing is like the cube function, right? So I got to do 3 times y squared plus t squared, right, times d dt of what? Inside function, y squared plus t. And I'm going to go ahead and write this in 2 steps to make sure you guys understand. I know for those of you who understand, you probably can write down my finished product, which I'm about to write, in one foul swoop, and that's great if you understand that. But if you don't, well, follow along here. So this is 2y. Derivative of y squared, right, is 2y, but what? Times dy dt. And the derivative of t is 1. So the differentiation's done. What's my next step? Yep.
What happens if you square?
Still in the marker. Thank you. Very good question. Okay, so then I got to solve for dy dt, right? So what does this give me? I get 6y times y squared plus t. This time I won't forget the square. Squared times dy dt is equal to 2t minus 3 times y squared plus t quantity squared. So what I did was to multiply this out and subtract the term without the dy dt to the other side. So multiply and isolate the dy dt term. Any questions? So dy dt is what? Two t minus 3 times quantity y squared plus t quantity squared divided by 6y times y squared plus t squared. And there you have it.
Do the second to last step to the last step again real quick.
So this gives me 6y times 6y times y squared plus t quantity squared times dy dt plus 3 times y squared plus t quantity squared is equal to 2t. Agree? 3 times 2 is 6. There's a y. There's a y squared plus t on both terms because it multiplies out, distributes. And then to get from here up to here, I just subtracted the term without the dy dt to the other side. Does that make sense? You got to keep the prize in mind. The prize is to isolate dy dt, right? Because once we do that, we can divide by its coefficient, and then we'll have, honest to goodness, just dy dt equals to stuff. And that's the answer for the moment. So why do this? Yeah, it's great. It's a thing we can do in math. What is this? What is the meaning of dy dx, or what's the meaning of dy dt here? It's the same as before, right? It's going to be the slope of the tangent line at the point x comma y, if that point's on the curve that we're talking about. So the next thing you could do with these examples is find a tangent line to a point that's on the curve. Can you guys, for example, tell me for this example number 1, what's a point on the curve? Can you find a point? Let's consider, what was our equation? X squared plus x y cubed plus y squared equals to 7. Can you tell me a pair of numbers which solves that equation? This is usually given to you in the problem, so don't sweat it. I'm just trying to make you guys do my job for me. I don't know. Let's put x equal to 0. If I put x equals to 0, what's y have to be to solve that equation? Just look at it. It's got to be plus or minus the square root of 7. So let's go with square root 7. So there you go. That's a point on the curve. And then the question that I have now is, what's the equation of the tangent line at that point to this curve? Tangent line is y is equal to the square root of 7 plus dy dx evaluated at the point 0 comma square root of 7 times x minus 0. Now this is new notation for us. What is dy dx evaluated? This big bar is the evaluation bar. It says plug in this point into that expression. So what is dy dx evaluated at 0 comma square root of 7? It's kind of a mess, right? So this right here means I go over here and I set x equals to 0 and I set y is equal to the square root of 7 and see what I get. Can you guys see? So what do we get? X is 0. Well, that's nice, right? I just end up with what? I get minus y cubed over 2y. Sorry, I'm running out of room to write that. So let's see here. We get dy dx minus the square root of 7 cubed divided by 2 times the square root of 7. Because the x terms are 0, you just get, looks like minus 7 over 2, yeah? Because the square root of 7's cancel, I'm left with square root of 7 cubed. Square root of 7 squared is just 7 minus 7 halves. So the answer then is the square root of 7 minus 7 halves x. There you go. That's the equation of the tangent line to that curve at that point. Sorry, this problem's kind of complicated, but mostly just because it's kind of the dy dx formula is kind of messy looking, right? But once you pick the tangent point you're thinking about, plug the point into the dy dx, that tells you the slope of the tangent line. The new wrinkle is that dy dx involves both y and x, right? Not just x. Would you like me to do another one of these? I probably should, right? How about this example over here? Can you guys find the tangent line and find the equation of the tangent line, really? Right? At what point? So you guys give me a point. What's a point on this curve? How about if I put x equal to 1? What does this give me? If I put x equal to 1, I've got what? 1 times y squared plus y is equal to 1. Can you tell me what I should choose for y then? I'm actually going to have to work at finding. If I make if I make the x coordinate 1, then the y coordinate, I'm going to have to solve this quadratic equation to find the point on the curve. Y squared plus y minus 1 equal to 0. I hope it has a solution. So that's y is equal to what? Minus 1 plus or minus square root of 1 minus 4, which is plus 4 over 2. So it looks like I can use minus 1 plus or minus square root of 5 over 2. That's just not at all what I want, guys. I mean, it's not wrong. It's just not pleasant. I don't want to make x equal to 0 again. That's too lazy. Yeah, fine, let me take my medicine. So minus 1 plus the square root of 5 over 2. Again, this part usually is given to you. The typical question is, here's a curve, here's a point on the curve, find the equation of the tangent line, right? So usually this point is given to you. So this thing I did up here doesn't usually happen to you. So what's the slope? What's the slope of the tangent line at that point? I'm sorry, it's too awful. Now I have to plug that into this. That's just, I don't want to do that to you guys. Stink. Now, scratch this. That's just too nasty to do today. You guys are tired. I can tell the rain has zapped your energy. You don't want to see that. Somebody find me an easier point on this curve. Are we going to go with x equal to 0 again? Fine. I'll be lazy. X equal to 0. What do we get? That gives you y equals to 0 as well, right? That's fine. So that is on the curve. And we can find, now that, look, we've gone from being too complicated, now probably to being so stupidly simple, it doesn't serve the purpose. So that's on the curve. Find the tangent line there. Find equation of tangent line. So first things first, we calculate the slope, dy dx. dy dx at the point 0, 0. So what I do, I take 1 minus 3 times 0 squared divided by 2 times 0 cubed. I'm writing these zeros, but I don't really need to, do I? I mean, you can see that the slope is what? If you plug in 0, 0 into dy dx, you get 1. You get 1 plus 0 over 0 plus 1. So the slope of the tangent line is 1. So what's the equation of a line with slope 1 that goes through the origin? Yeah, I heard y equals to x. There you go. That's the tangent line. Well, I'll tell you what. You guys go try to do the homework problems on these, all right? See if you can make sense of them. If you can't, you come back, start our next class. You can ask me about it, all right? But to summarize, you implicitly differentiate, and you simply plug in the point you're interested in into the dy dx formula. That gives you the slope of the tangent line. And then you're just back to where we were before, right? The equation of a line with slope and point. All right. So that's all I have to tell you about implicit differentiation. Don't get too excited. We still have more to do. You're like, are we ending class now? Yes. Hope springs eternal. No, we need to talk about related rates. All right. So, related rates. Is an application of implicit differentiation, where typically what we were using as x here is replaced with time t. T is the independent variable. And so here's a typical example or two for you. All right, so example 1. Suppose that air is blown into a balloon, which is spherical, at 3 inches cubed per second. All right, so you're blowing up a balloon 3 cubic inches per second. Every second, you're putting 3 cubic inches of air into the balloon, all right? If the radius of the balloon is r equals to 10 inches, then how fast does r increase? At that moment, of course. At that instant of time. All right, so in every related rates problem, the first thing you have to figure out is what is the relation between the quantities in play? Like what are the quantities that make this word problem what it is? Well, there are two things: volume and radius. What's the relation between the volume and the radius? Well, I told you it was spherical, right? So, fun fact for you, which maybe you didn't know before I tell you this, but now that I've told you, you should remember this, okay? So the volume of a sphere is 4/3 pi r cubed. If you want to see why, stick around here for the hour after, about a month from now. Calculus 3, I'll work it out. It's kind of fun. It's not that hard. Anyway, this is, for us, just, it's like something the Pope told us. It's got authority. It's just like, Oh, I'm sorry. We don't believe in the Pope, right? Or do we? I don't know. I guess you could be a Muslim here too. Why not? I mean, sure. There's no problem with Islam. It peacefully coexists with all the religions. So, I don't know. Just no problem. Okay, I digress. Like what? So, now there's something else here, though, more fundamental and philosophical, before I start making other comments about world politics and so forth and so on. What can you say about the volume and the radius here? Are they functions? They're functions of something else. What are they functions of? Each other. Well, that I gave you that here. But more fundamentally, time. Right? They're functions of time in this problem. The volume and the radius are changing with time. So really, we have implicitly v is equal to v of t, and r is equal to r of t. Now, there's an explicit subset of these related rate problems where you can actually, honest to goodness, find the function of time. But usually it doesn't really matter what that function is. It just matters that it's there, because if it's there, then you can do implicit differentiation. I can differentiate this equation with respect to time, is the point. So now we're actually we're doing what we've been doing all today, which is an implicit derivative. So what's that give us? That gives us dv dt is equal to 4/3 pi times what? 3 r squared times dr dt. Oops. Sorry, I was about to put a vector on the r. That's a different class. All right. So what's this given? Now, let's think about it. What are we given in this problem? Given the radius. What else are you given? Yeah, we're given that the radius is equal to 10. We're also given that dv dt is what? Now, I didn't tell you dv dt equals something. That is up to you to interpret. I told you that the air is blown into a balloon at 3 inches cubed per second. That means that dv dt in inches cubed and seconds is 3. What are we trying to? What are we actually trying to solve for here? Think about it. What's the question that I asked? What is that in terms of calculus? Rate of change, right? This is interchangeable with dr dt. So what we want to solve for is dr dt. These aren't hard. You just have to think through them. So dr dt is what? The 3's cancel, right? We get dv dt divided by 4 pi r squared. And then plug in the values. So that was 3 divided by 4 pi times 10 squared, whatever that is. Apparently 3 over 400 pi. That probably means about as much to you as it means to me. Now this is in inches per second, because I've used inches per second in my calculations, right? If I had brought my calculator, I could give you a decimal. I'm not sure whether WebAssign wants exact answers or decimal answers, but we'll figure it out as we go, right? No big deal. I mean, I kind of like it. I would kind of like a decimal answer because I can understand that more. 3 divided by parentheses 400 times pi gives me about, it's given me in scientific notation, fine. Convert that. It's about 0.00239 inches per second. Which makes sense if you think about what is the volume of what is actually the volume in inches cubed if you have 10 inches? So guys, the volume at this problem, we're blowing into the balloon at 3 inches cubed per second. What is the total volume at the moment the radius is 10 inches? Do you guys know?
When you plug it into the formula.
Right. I'll tell you, I worked it out. It's 4,189 inches cubed. So of course, if you have over 4,000 inches cubed and you're just increasing at 3 inches cubed per second, it makes sense that the radius is barely changing, right? You're not really adding much to the net volume. You're not changing the radius very fast in this problem. Questions?
How did you get rid of the 3 under the 4 over 3 with
Oh, the 3 over 3 canceled because I got a 3 from the differentiation of r cubed. Give me 3r squared dr dt by the, chain rule, right? So these 3's cancel. And that 3 came from differentiating r cubed. Of course. I do all math in my head. Where else would I do it? I don't know. Sorry. I know what you mean. I'm just being a third derivative. Oh, I forgot you guys asked me what the application of the third derivative was the other day. The third derivative is called jerk. So if you want to be like really opaque, you can just tell somebody, you're such a third derivative. Well, when you study physics, mass times acceleration is equal to the force, right? So acceleration is like the second derivative. So the force is, roughly speaking, the second derivative, right? The change in the force, which is kind of what you experience when the force changes, that's like a jerky motion. And so it's called the jerk. For example, if you've ever been on a train and gone from a straight section of track to like a curved section, as you make that transition from straight to curved, all of a sudden there's like this, that'd be a place. All right, another example. How about this? Let's suppose, standard example, we've got a ladder. All right, and the ladder has length 10 feet. And let me suppose that it is, I don't know, golly, 6 feet this way, right? And let's suppose that it's falling without slipping, and suppose that the bottom of the ladder is going at 2 feet per second that way. The question then is, how fast does the top of the ladder slide down the wall? Now we are assuming that this is not some kind of weirdo wall at some odd angle. This is a right triangle. So we're going to have to use some of that right triangle trigonometry that you hopefully learned back in the day. Do you guys understand the question? So we need to invent some labels for things in this problem, right? Let me suggest that we use x for this distance here. And let me suggest that we use y for that distance there. All right? So x and y in this problem are functions of time. Right? X is not fixed at 6. We should think about x varying. Right? X equal to 6 is the point at which I'm asking the question. how fast does the top of the ladder slide down the wall, parentheses, when x is equal to 6 feet. All right, so there's the problem. What should the first thing I do? The first thing I need to do is figure out what's the relation between the variables, right? What's the equation that relates the variables given this setup? Pythagorean theorem, right. So what is that here?
6 squared plus y squared 10.
We need to think of x as a variable, though. So you don't want to assume, don't plug in this data at the start. If you do, it leads you to wrong answers. But that's the fundamental mistake people make. That's the go-to mistake here. Now, why do I know this is 100? Right, the length of the ladder is not changing. I suppose you could give a more interesting problem where you have a variable length ladder, and then you'd have a function of time on the other side. But, there's another instructor here who likes to put this at an angle. So then you have to use law of cosines for the triangle. But this course has a trig lobotomy, as you may recall, so I'm not allowed to do that. Yes, we have removed trigonometry from our mind. Chop! Chop, chop. There's our relation. Now we can do what? I guess we can take a moment, smell the roses, think about what we're given. What are we given? We're given that x is equal to 6. And so what's that tell us about y? Y squared is 100 minus 36, which is 64. So therefore, y is equal to 8. You're like, why is it not minus 8? Well, why is we think about x and y being positive because of the setup of the problem, right? So apparently y is equal to 8 where we're interested. And what are we actually trying to find? What's our goal to find? What are we actually trying to, in terms of calculus, what are we trying to calculate? What is this? How fast the top of that means calculate what? That's what? The rate of change of y, right? That's dy dt. What are we given? We also know that dx dt is equal to what? Yeah, 2. Feet per second, of course, but. All right, so then what do we do? Differentiate the relation, which gives us what? 2x times dx dt plus 2y times dy dt is equal to 0. And then solve for what you want. What do we want? dy dt, right? So dy dt is equal to minus 2x dx dt divided by 2y. And then just plug in what we're given, right? What are we given? Well, the 2's cancel. You can cancel the 2's. X is 6, though, so I got minus 6 times 2 divided by y was 8. 12 over 8. 1.5? Yeah. And I'll put back in the units. It's feet per second, right? So the rule for me in here is this, guys. You can do calculations without units, but I do want your answer to have proper units on it. I mean, I'd like that. Is that too much to ask?
Why is it negative?
Ah,
Why is it negative? Why is it negative 1.5?
because it's falling.
Okay.
Yeah. Because the value for y is decreasing. Y is getting smaller. So we should expect that minus, yeah. Now it's a question of language, right? If I said how fast is it decreasing, you could say that the rate is 1.5. But I'll try not